So we had introduced, at the end of last lecture, we had started looking at nuclear fission and had actually done some calculations for availability of energy from nuclear fission of uranium-235. So quick review here. Here's uranium-235. We can set off these fission reactions pretty reliably using a neutron. Now that's a really interesting feature here. There are only, you look across the periodic table at all the elements and all their isotopes, there's only a handful of isotopes that reliably undergo fission. And it turns out that uranium-235, that particular isotope, is one of those materials. Now it turns out that another material that reliably undergoes fission, there's like two really common materials that we use, and the other one is plutonium-239. Now also in the previous lecture we had looked at this slide, but let's review that again. In nature, if we look at the uranium that exists in nature, naturally occurring, a little more than 99% of that is uranium-238. 238 is not available as a fission fuel. Uranium-238 does not undergo fission. So less than 1% of the uranium that we find in nature is uranium-235. Now, the uranium-235 can be used as a fuel in a nuclear power plant. The uranium-238 can't be used as a fuel. So when we collect 1,000 kilograms, a ton of uranium, only about 1 kilogram of that is available as a fuel. What if I could take the remaining 999 kilograms in that ton of uranium and convert it into a fuel? I'd have 1,000 times as much fuel from that uranium. And that's what this process allows us to do. What you can do is that you can put uranium-238 into a power plant with uranium-235. In fact, most of the uranium that goes into a power plant is actually uranium-238. We don't enrich it very much. We don't need to. But you can adjust conditions inside a nuclear power plant so that some portion of the neutrons, rather than setting off fission for the uranium-235, they are actually being absorbed by uranium-238. So if you adjust conditions so that the neutrons are traveling a little faster, what you can do is you can generate plutonium-239, which is also a fuel. So in a power plant, you can actually be running off the uranium-235, but at the same time generating additional fuel, the plutonium. And so we can keep putting more and more of the uranium-238 in there. And again, the comparison or the numbers would be, you get a ton of uranium, initially only 1 kilogram can be used for fuel, but using this process, the remaining 999 kilograms could be converted into fuel. So that means 1,000 times as much fuel available for nuclear power plants. Now, as you guys know, the downside for nuclear fission power plants is that everything coming out of the fission plants is radioactive. So we're stuck with the radioactive decay products, or the radioactive products of fission. So not decay products, but fission products are all going to be radioactive. And so if you choose to go the nuclear fission route for energy generation, you have to be ready to deal with having tons and tons and tons of radioactive material that's going to need to be stored safely and reliably for many generations to come, thousands of years into the future. So it's a decision you're making that involves, again, thousands of years into the future. So this was kind of outlining what we think of as fission looking like, the uranium nucleus splitting. Here is an example of one of those reactions. And well, let's take a look. I guess we had run through the numbers here. So this was the reaction that we were looking at, the 141 xenon and the strontium-93. Those are going to be radioactive. And they're going to be radioactive because there's just way too many neutrons. If I take something from far, far into the periodic table, like uranium-235, it's going to have a number of excess neutrons. It's going to have a lot of extra neutrons to stabilize the nucleus. If I now split it into pieces that are more in the middle of the periodic table, there's just going to be way too many neutrons. So this is going to have excess neutrons on it, and it's going to be radioactive. This is going to have extra neutrons on it. That's going to be radioactive. And even then, they're going to be left over just individual neutrons coming off. So you're getting these enormous amounts of energy, 180 MeV of energy, but you're generating radioactive materials. Now, in these nuclear fission reactions, I've tried to be very careful. I don't want to say that in fission, the nucleus splits in half. It turns out that only 1% of the time or something does it actually split in a region near 1/2. Most of the time, it ends up in some piece. One of the pieces is somewhere around 135, 140, and the other size piece is somewhere around 95. So just something to be aware of. It kind of splits asymmetrically. The two pieces coming out tend to be large, but it doesn't split in half so much. Kind of an interesting feature of fission. Here's a diagram outlining how the chain reaction would take place. So again, if the kind of red, pink circles here, spheres, are uranium-235 nuclei, then we set the reaction off with a neutron. Once we set the reaction off, we're getting these fission fragment products coming out, but we're also getting additional neutrons. And as long as we can get just one, every time a reaction occurs, if at least one of those neutrons sets off another uranium-235, that will sustain our power plant. Now, if you set up the uranium-235 in a way where you just try and get the reaction to exponentially increase, so the idea here would be, well, in this case, for every reaction, we're creating enough neutrons to set off 2 more reactions. And then each of those creates enough. That would create an ever-increasing chain reaction, and that's used in nuclear weapons. So in nuclear weapons, we use much higher concentrations of uranium-235, and the idea is to set off as many of those reactions as rapidly as possible before the uranium-235 gets blown away by the initial reaction. So I guess unfortunately here again what we found is that it's easier to develop with these nuclear processes of fission and fusion. It's easier to develop a weapon than it is a power plant. The weapons, you just try and set off as many reactions, make the conditions extreme, and set off these chain reactions. Now in nuclear, that's a lot to read on this slide, so let's not read it. What are the key features here? I'm going to say everything in here comes down to the reaction works better if the neutrons are moving more slowly. So we can put materials like graphite or water into the reaction, the nuclear reaction, the fuel rods, surround those with graphite type materials. It slows the neutrons down, and then it makes the efficiency higher for fission processes for uranium-235. So with that, what we can actually do is, even naturally occurring uranium-235 is less than 1%. It's only about 0.7% of naturally occurring uranium. That won't sustain a reaction, but we don't have to enrich it very much. If we can get a uranium sample enriched up to where 2 to 3% of the uranium is uranium-235, that's enough that we can build a power plant and operate with that uranium sample. So we never have to bring it up to weapons grade, much higher concentrations. And that's how you can tell the difference between uranium that's being used for a power plant versus uranium that's intended for the development of nuclear weapons. This diagram's just pointing out that, we set off a reaction, here come the neutrons. If the neutrons leave the area where the uranium is located, then the reaction stops. If you're losing a lot of neutrons to the environment, they're not setting off additional reactions. And that's referred to as critical mass. So critical mass refers to the amount of fissionable material, either uranium-235 or plutonium-239, that you would need in one location so that the reaction would be self-sustaining. Here's a diagram of what a nuclear fission power plant looks like. Now, there's a lot of these around the planet, right? We've been building nuclear power plants since the 1950s probably, and generating electricity. And with the exception of a few power plants, that whole operation has gone pretty well. Again, the downside is that we've generated thousands of tons of radioactive material now that we're still not sure how we want to store that. And then along with that, we have had a handful of reactors that have catastrophically failed. They have not set off a nuclear detonation, but the core, we have failed to be able to keep the core cooled, and the cores have overheated, the material in the core has vaporized, and the increased pressure from inside the reactor containment vessels has split open some of the containment vessels, and vaporized radioactive materials have gone out into the atmosphere. So this happened at Chernobyl in Ukraine. This happened with the Fukushima reactors in Japan. And then there have been some other close calls, like 3 Mile Island in Pennsylvania. So the plus side of this is you're not generating CO2, you're not contributing to global warming. You're getting a lot of energy from a little bit of fuel, but when these reactors fail, it can be catastrophic. All right, here's our reactor core. So those little fuel rods, the little black rods there, fuel and moderator are built. I guess those are the control rods. So they've put some fuel rods down inside this moderator, and they put some other rods inside that will absorb neutrons. So the way you shut down these reactions is in an emergency, you drop a bunch of, I think it's mostly boron, into the reactor, and those have a very high absorption rate for neutrons. They absorb all the neutrons out of the reaction and shut down the fission. So now again, in the Fukushima plants that failed several years ago, during the earthquake and tsunami, that part of the shutdown worked perfectly. So the earthquake happened, the control rods went in, absorbed all the neutrons, fission shut down, but the core is full of radioactive leftover materials from the reaction, and those radioactive materials continue to undergo radioactive decay and heat the core. Now, during normal operations, there's water or some other type of coolant being pumped through the core to draw out that thermal energy. But in this case, the pumps shut down. There was not a backup power supply for the pumps. There was nothing to keep the cores from overheating. So the cores overheated from the heat being generated by radioactive decay, not from fission, and materials within the core vaporized. All right, so here is the essentially combustion chamber. Here's the reaction vessel where the fission is taking place. We're pumping water through. The water coming out is at really high temperature. So you've got this extreme high temperature pressurized water or pressurized steam. That's taken through a second exchanger to keep it isolated from the reaction vessel itself. So to make sure that none of this water could be it could be slightly radioactive. Since it's going right through the core, there's going to be a lot of neutrons coming through that water. The water could be picking up neutrons. You could be generating radioactive isotopes. So we pump that through a heat exchanger and generate another set of steam, which is run through our turbine, goes through a condenser, comes back into here, and it generates electricity. Here's our electric generator from Physics 4B, and here is the steam turbine. So how does this compare with power being generated in, say, a coal-fired plant? And if this was an electric plant based on coal, then instead of the nuclear reactor, you'd be running a chemical reaction just using carbon. Carbon plus oxygen from the air, generating CO2, and all of the product in that case, essentially 100% of the product would be carbon dioxide coming out from a coal-fired plant. So it's not so different. It's still a heat engine. It's still going to be limited in efficiency based on the thermodynamics that we looked at back in Physics 4B. And then here is the electricity being generated. All right, here is a picture of the Chernobyl power plant. And you can see that that was a pretty catastrophic explosion, really, of the power plant facility. Now, this reactor had started off as an early experimental reactor, and no one ever went back and built a heavy-duty containment vessel, which I don't know what effect that would have had. So this was not structurally nearly as durable as today's nuclear power plants are. But again, the reactors in Japan and Fukushima, those failed. The containment vessels there also failed. So here's a problem for us to take a look at. It's saying, let's say that we build a power plant. We're going to operate it at 1,000 megawatts. Now, 1,000 megawatts is just it's a modest-sized power plant. This is not a large-scale power plant, but still, that's a good amount of power. So we're going to have a power rating on our power plant. It's going to be generating 1,000 megawatts of electrical energy. So, and we want to run that for a year, and we have a thermodynamic efficiency, chapter 20, of 33%, and we're going to be using uranium-235 for our fuel. How much uranium should we order? So let's take a look at that. Here's my picture of a power plant. So here is my 1,000 megawatt power plant, and that's the power rating. And here are the electric lines coming out of the plant. So let's first of all look at the number of 1,000 megawatts. Now, a watt is a joule per second. So megawatts is the rate at which energy is being generated. And so that's ongoing for the whole year. If that power plant stays online the whole year and maintains kind of a steady rate of energy production, we're going to say that's a 1.0, 10 to the 9th joules per second is the rate at which energy is being generated. Now, in order to calculate an amount of energy, I have to put in a time period. And the time period they gave me was 1 year, and 1 year is like 31.6 million seconds. And remember, we got an efficiency rating of 33%. Now this, for some reason, these efficiencies are it's easy to get that backwards. So here's my recommendation for carrying out these calculations. I want to find out how much energy this power plant produces in an entire year. I'm going to start off with 1 year. So 1 year is 31.6 times 10 to the 6 seconds. Now, the rate at which electricity is being generated is the power rating for the plant. If it's a 1,000 megawatt plant, it's generating 1,000 megawatts of electric power. And so I'm putting in my 1.0, 10 to the 9th joules per second of electric energy. And then to get the efficiencies right, what I want to do is get the electric joules to cancel. And a 33% efficiency rating would say, in order to generate 33 joules of electricity, I need to generate 100 joules of thermal energy. So what this power plant's doing, it's just generating a bunch of thermal energy, right? And that's how I make sure that I get this ratio right. I'm going to say on midterms, it's kind of 50-50. Half of students get this put in the right way, half of them get it backwards. So something to pay attention to. So it says that the total energy, and I apologize for this too, total energy for the year of thermal energy that I'm going to need, because that's what the fission is going to give me, is just a bunch of hot water. The thermal energy that I'm going to need, 9.58, 10 to the, that's a 16. So that's, about 10 to the 17th joules of thermal energy for the year is how much I have to produce. So here, 9.58, 10 to the, and somehow I did that twice. So again, that is a 16 right there. 9.58, 10 to the 16 joules. How much uranium-235 do we need to generate that amount of thermal energy? So 9.58, 10 to the 16th joules. I'm going to convert that into MeV. This is my MeV converter right here. Remember, it's MeV, not EV. So the conversion is 1.60, 10 to the minus 13 joules, not 10 to the minus 19, which we're used to writing down, but 10 to the minus 13 because it's MeV. And then I'm going to use the number that we just calculated. We went and did that Q calculation in an earlier example and found out that for that particular fission, we were getting 180 MeV, and that's a pretty typical number. So if you run these Q calculations for fission reactions, you're getting like 180 MeV roughly, on average, in fission. And then what we can do is use the molar mass of the uranium-235. So since it's uranium-235 specifically, I know that its molar mass is going to be 235, 0.0 something something something. So that's not necessarily something you have to look up. I can get 3 or 4 significant figures just by using the 235.0. So what that gave me when I calculated all this is 1,300 kilograms of uranium-235. So let's stop and think about that. This was a modest-sized power plant. I'm going to operate it for an entire year. I'm going to be generating lots and lots of electric energy and making that available. And I only need to order 1.3 tons of uranium for the year. 1.3 tons of uranium is like nothing. I mean, if this were a coal power plant operating on combustion of coal, how many train loads of coal would have to come through the plant every day? We would be dumping tons of coal into that plant. It turns out, kilogram for kilogram, fission produces like 1,000,000 times as much energy as any chemical reaction. We would need 1,000,000 times the mass of some fuel if we were running a chemical reaction like the oxidation of coal. So that's extraordinary. And numbers like this are what have enabled submarines, for example. There you go, ships in the Navy. So a submarine, before the advent of nuclear power, of fission, submarines could only go under the water for hours at a time. They really couldn't stay down very long, at least not if they're powered, because when submarines were running off of, say, internal combustion engines, oil or gasoline, something like that, you have to have oxygen for those reactions. So even more so than oxygen for the crew to be breathing, you need a lot of oxygen. You can recycle enough, you can generate enough oxygen for the crew to breathe, but you can't generate enough oxygen to feed the engines. So with the advent of nuclear fission, you could put, a small-scale nuclear power plant, fission power plant, inside a submarine, and they could stay down for months. So the first nuclear-powered submarine in the U.S. Navy was called the Nautilus. Had a chance to go through it a few years back. It is now in a museum in Connecticut. But they built this thing and they operated it, and they at one point took the submarine and they took it underwater to the North Pole. Just stayed under the water the entire time. So that's an easy way to get to the North Pole, is just go into the Arctic Ocean and take a submarine there. No need to come up. Plenty of oxygen availability from oxygen storage for the crew. You don't need any oxygen to run these types of reactions. And you don't need much fuel. So, a little over a ton of fuel is going to operate this power plant for a whole year. So, kind of remarkable. One last, a couple last items to look at, actually. With this idea of what is power and what is energy. So I always tell my students, with your science background, your science and engineering background, if you guys decide you wanted to go into journalism, might not be a bad field. And I say that because, kind of watching a lot of the science presentations on news programs. A lot of times when I read news in science, just kind of, general news sort of broadcasts, the science isn't well understood by a lot of the journalists that are out there. So whenever they're talking about power plants, so from time to time you've got some kind of a story on power plants. And the standard line here is, well, what's the rating on your power plant? And they say our power plant produces energy at a rate of 4,000 or 5,000 megawatts. And the response is that for one day or is that for the year? And the answer is, well, it's a power. So the power ratings are telling us the rate at which energy is being produced. And that's just ongoing. In order to compare amounts for a year, you wouldn't be asking a power question. You would be asking an energy question. What's the total amount of energy generated in a year? So, just this notion of power versus energy, make sure you're clear on it. And I think you've got a career in journalism out there waiting for you, possibly. Just another quick example. When was it? A year ago, I guess, on PBS, on public broadcasting, they held a story about a group of they were calling themselves scientists that had developed a new technique with fuel cells, and they said that they had developed a way to dissociate water that required no energy at all. So you could take water, separate it not using any energy, and then take the hydrogen and oxygen and recombine it and generate energy for basically nothing. And they had some kind of a bogus device sitting there where they would pour the water in, and then they would hook up wires to it, and it would light things up. And I'm thinking, there's just a battery inside. It's totally made up. And they actually broadcast a story on that, and a few nights later I noticed they retracted that. They apologized. They had been taken in by this. So anyway, with a good background in good understanding in science, I hope that in journalism that they're always looking for really qualified people that understand the science behind things. One last item with this power plant. We came up with this number, 1,300 kilograms of uranium-235. And I was just curious, if it were one solid block of uranium-235, how big would it be? And so I looked up the density of uranium, and it turns out uranium's really dense. Uranium's about as dense as gold, and of course I don't know if anybody there's picked up a block of gold. I never have. This is like 3 times the density of steel. So, the same size of uranium compared with steel would have 3 times the mass. Anyway, really dense. And so I took that mass, the 1.3 10 to the 6 grams, and determined that 1,300 kilograms of uranium would have a volume of 68,100 cubic centimeters. And then I imagined that volume to be a cube, and solved for the distance along one side, 40 centimeters. So if I have a piece of uranium that's like, 40 centimeters is like that. If I have a cube this size of uranium-235, that's enough to power this, modest-sized power plant for the entire year. So not a lot of uranium-235. Now you don't want to store the uranium-235 as concentrated. If you're bringing in the fuel for the year, it's going to be made into fuel rods. So if you're making this into fuel, you're not going to want to concentrate it, because if by chance a stray neutron comes by, it's going to detonate all that uranium-235. Doesn't sound like a good idea. So whenever you're transporting any uranium-235, it's created in little tiny pellets, and then it's immediately, it's surrounded with moderator materials that will slow the neutrons. So you don't want the reactions being set off. You don't want this occurring outside of some type of a containment vessel. All right, there was our fission power plant. So this is just pointing out that nuclear weapons, early nuclear weapons, were based on fission. In fact, all of our nuclear weapons today also start off using fission reactions. Okay, so kind of what we had talked about before. Now, here is this, if you remember from the previous chapter, chapter 41, we had looked at this very same diagram, and what it's saying is this is the binding energy per nucleon, and the most stable nuclei are in the neighborhood of iron 56. So a lot of times we point to iron 56 as the most stable combination of protons and neutrons in nature. So that says that when we start off with something like uranium-235 and we split it into two smaller pieces, in this range somewhere, well, these binding energies are going to be much larger. So what we've done is we started with something that was reasonably stable, but we split it into two pieces that are considerably more stable, and that's the difference in terms of energy. So fission can be thought of taking these heavy isotopes and splitting them and creating products that are actually more stable. And there's only a handful of materials, of isotopes, that reliably undergo fission. Now in the other direction, what this table is also telling us is, hey, in the opposite direction, if I start with materials like individual protons, or deuterium, tritium, helium-3, you can see some of these materials, as we fuse them together, if we were able to run reactions to start with very simple nuclei and then combine them, that we could go from really low average binding energies up to really high binding energies pretty quickly. And that process is called nuclear fusion. So fusion is starting from those lower elements with not such high binding energies and creating things that have much higher binding energies. So our first example, nuclear fusion. Let's take a proton. Now I know it's listed as hydrogen 1, but remember, we're just thinking of a nuclear reaction here. So we're going to take a proton, combine it with a neutron, and we're going to create this isotope of hydrogen, deuterium, is the name. So remember, the isotopes of hydrogen have names because we talk about them so frequently. So the H2 isotope is called deuterium, and the H3 is called tritium. And the H1 is called protium. So they all three of them have names. And in this reaction, we start with protium, one proton, and we form deuterium, where a proton and neutron are overlapping each other. So they have wave functions that overlap. And they're saying how much energy is released in this reaction. Now notice in this reaction, we're also creating a high energy photon. There's a period here. I don't know why they put periods in. I don't think those are really needed. But that's a photon that's being generated. And a reason for that is, let's think about what happens in fusion. If I take two objects and I run them together and run some kind of a nuclear reaction, and I release a lot of energy, that says that whatever I've created, it can't just be sitting there. If there's just one object at rest, there's no energy release. And so what happens is, in the products, we always have to create at least two products coming out. And in a lot of these reactions, the other particle, the other product coming out, is a high energy photon. So in this reaction, that's it. So I'm taking a proton and a neutron, they come together, they form deuterium. There's a lot of kinetic energy, so the deuterium that comes out of that reaction heads off in some direction, but there's a photon that goes in the opposite direction. So momentum is conserved as well as overall energy. So a lot of times we just throw a photon in, that's what's going to be happening as one of the products. Now it wants us to go in and calculate energy for this reaction, how much energy is released. We can do that. So we've been doing a lot of these Q calculations, and now we're going to do it for a nuclear fusion process. So here's the proton. Now remember, for the purposes of calculating Q, I want to put in all neutral species of nuclei, because the masses are going to include their electrons. I want the electrons to balance. So I'm going to write the proton as hydrogen 1 and use the mass of hydrogen 1 plus a neutron becomes deuterium and a photon. And then these are all the masses that I looked up. So hydrogen and deuterium masses, there they are. Of all the isotopes of all the elements, it's the hydrogen isotopes, H1, H2, and H3, that have the largest proportional difference from an integer value. And the reason why is this. What we saw back in chapter 41 is that when you add up all the protons and neutrons in a nucleus, it's always a higher value than the mass of the nucleus itself. So once the nuclear force comes into play, we have what we call missing mass. So there's this nuclear binding energy, and that shows itself as a reduction in mass. A proton all by itself has no binding energy with other nucleons. So that puts it at 1.078, almost 1% higher than the integer value. Same thing with deuterium. Even though deuterium has a little bit of binding energy to it, it's not a lot. The existence of deuterium is just barely stable. And so there's not a lot of binding energy here either. Same thing for tritium. So you'll see that in some of those, it may not be enough to just go with 3 sig figs and say it's exactly an integer, because that next number doesn't round down, it rounds up. Same thing that we're seeing here, that already has a 2.01 in it. So something to be aware of. Here's the neutron mass, here's the photon mass, that was easy. So we'll just put in a bunch of zeros, and then I did a Q calculation. So here's my calculation of Q, all the stuff we started with, subtract off all the stuff that comes out, and it says that there is energy released, and it's this much mass, which is equivalent to this much energy. So that's not bad, 2.22 MeV of energy released in the formation of deuterium. And that's about as basic as you can get in terms of a nuclear fusion reaction, 1 proton, 1 neutron. Now, you guys are probably aware also that maybe the most prominent place where a fusion reaction is going on in nature is inside stars. So these are the reactions that go on inside stars. Now, we'll see in chapter 44, we'll talk more about nuclear fusion reactions going on inside stars. But what we find is, at least initially for all stars, whether they're low mass stars or kind of medium-sized mass stars or large-scale high mass stars, all of them start off with a set of reactions that look kind of like this. So now these are all going on at the same time, and they're all going on inside the core of the star. It turns out that, well, we can go in and do some calculations. We'll see what the electric force barriers, the potential energy barriers are for these reactions. We looked at reactions earlier, we calculated energy barriers, and we're going to find out that for all these reactions, there's going to be an energy barrier. Protons coming together, they're going to repel each other, it's going to be hard to get them close enough together to set off these reactions that we're trying to generate here. In addition, this reaction in particular, this very first one, now this is the formation of deuterium, but it's not using a proton and a neutron. Stars don't necessarily have a lot of neutrons available for running fission reactions. Neutrons, it turns out, are not stable. Neutrons left by themselves only have a lifetime of about 10 or 15 minutes, and then they decay into protons, neutrons, and protons, electrons, and neutrinos. So the fuel that we're using here is primarily protons, and so we're starting with a couple of protons. In order to form deuterium, during that process, one of those protons has to turn into a neutron, kind of like in beta plus decay. So I've got protons turning into neutrons along the way. Now, once neutrons are inside nuclei, then they're stable because of the binding energies of the nucleus. So a neutron comes in, it combines with other protons and neutrons. Now, in order for that neutron to decay, it's going to disrupt that nucleus. So the binding energy, the combined binding energy within a nucleus, maintains the neutrons. They don't decay if they're in a stable nucleus. All right, so that's an especially difficult reaction to set off. This reaction, you have to be patient, because not only do you have to get two protons coming together at really high energies, but you have to wait around for the weak force to take effect. These other reactions, these fusion reactions we're looking at, those are based on the strong force. What the strong force does is it just rearranges the protons and neutrons that are already there. And strong forces occur at a very high rate. Weak forces don't. So weak forces, you have to be patient. Now, stars are patient. So inside the core of a star, where it's really high temperature, conditions are extreme, and you are going to get a sizable number of these reactions happening. Another kind of interesting feature here is, where did all the neutrons that you're made out of, or what did all the neutrons that planet Earth has in it, how did those neutrons come about? And those neutrons were all formed in that reaction, inside stars at some point. So again, all of the elements that we have beyond hydrogen, really, either occurred early on during the first 3 minutes of the high density, high temperature plasma state that the universe was in. So a fair amount of helium was formed during that time. Since that time, additional neutrons have been formed inside stars using that reaction. And what that reaction has done is it's taken neutrons, locked them inside a nucleus, and now they're going to be stable. And then additional fusion reactions inside stars take those protons and neutrons, take the deuterium, and turn it into heavier and heavier elements. So all the neutrons are coming from there. And it's not especially energetic. That's not an especially energetic reaction, because it's not a proton and neutron now, it's two protons, and you don't have as much mass to work with. So two protons barely have enough mass to run this reaction. All right, the other reaction that goes on inside stars, here's a proton combining with an existing deuterium to form helium-3. So that reaction also is ongoing. And then two of these helium-3s that have been produced can form a helium-4, and then a couple of protons fall off. And those protons can recycle now, and they're available to run these reactions. So it's kind of like all three going on at the same time. Now in this diagram, they have gone through for us, and they've calculated the Q values for each of these reactions. So let's see what the overall effect is if these three reactions are kind of cycling through simultaneously inside the core of a star. So here it is, stellar fusion, and these are the reactions going on in the sun, right? So if you ask, where is all the sunlight coming from? How is all that energy being generated? These reactions aren't producing the sunlight. The light coming off of the sun, off of stars, is generated within the first, I don't know, 50 or 100 kilometers of the sun. It's only that very outer layer. The light we see is coming from the outer layers, so it's being generated just from the high temperature. What we're talking about here with stellar fusion is happening deep inside the core, and deep inside the core you're just generating a lot of thermal energy, and that just heats everything up. So here are those processes of nuclear fusion. Now what we can do, if you look at that previous diagram, there were these three reactions that are referred to. So let's do this. Let's run this reaction twice, and this reaction once. Now by running this twice, I'm going to generate some anti-electrons, some neutrinos. The neutrinos are just going to fly off, and a couple of deuteriums. Now I put plus signs on here just to remind us that at the core of a star, there are no electrons attached to nuclei. It's all plasma. The temperatures there are so high, electrons are not combining with nuclei and forming atoms. Everything's just existing as some number of nuclei and some number of atoms zipping around. And so this is really proton plus proton becomes deuteron plus anti-electron plus neutrino. And if I run that reaction twice, I'm going to get two of these neutrinos, which fly off, two anti-electrons, which we'll come back to, and then two deuteriums. In the second reaction, which I'm also going to run twice, I take those deuteriums, and for each one of them, I add an additional proton on. Now what that gave us was helium-3 nuclei plus a high-energy photon. So we're seeing photons are being generated. Now the photons are going to stay, the energy of the photons are going to stay within the sun and raise its temperature. The neutrinos aren't. So whatever new energy the neutrinos come out with, and that's not especially energetic, those neutrinos are going to be flying out of the sun. Now you may have seen some of these disaster movies. I think there was a movie called The Core. Maybe it's been a while, maybe it's 10 years now. But in The Core, I think that was the movie. Maybe I've got this, maybe it's a different movie, but there was, in the plot, the idea was that researchers, astrophysicists, knew that the sun's nuclear fusion was shutting down, and that was because the production of neutrinos had stopped. So I thought that was an interesting plot to throw in there, because if nuclear fusion reactions shut down in the sun, how long would it be until you would stop seeing neutrinos? And that would be immediate. The neutrinos that are produced in these reactions, well, neutrinos don't really interact very well with anything. And so neutrinos, for the most part, are going to make their way all through all the layers of the sun. They're going to head out into the solar system, and we can detect that immediately. So if the neutrino production dropped off, if nuclear fusion did shut down, we would know about that right away. Now, what about these other things? What about the energy, the thermal energy that's being generated? And the thermal energy takes, it's like tens or hundreds of thousands of years that the energy at the core makes its way out to the surface and generates a bunch of photons. So the neutrinos would be that immediate direct information that fusion has shut down. It might be a while until we see that affect the temperature of the sun. Temperature of the sun, I guess, would drop off gradually. All right, so we're going to run this twice. We're going to get two of these helium-3s, and then we're going to take those two, generate a helium-4. Now, helium-4 turns out to be, between helium-4 and heavier elements, there's a bit of a gap. It turns out that there are not very many stable isotopes in between helium and carbon. If you look at those elements beyond helium, things like lithium, beryllium, boron, until you get to carbon, lithium, beryllium, and boron don't have the same high binding energies that helium and carbon have. So it creates kind of a barrier for these stars. The stars are running these reactions and they're getting as far as helium-4, but at the temperatures inside the cores of these stars, additional fusion reactions aren't going to be possible. Stars are going to have to go to much higher operating temperatures in order to continue this process of fusion. And only the high mass stars are able to do that. So anyway, this becomes kind of a stopping point. So it's like you're generating a bunch of helium-4. So let's take two of these, one of these, and combine them all together. Now what I'm doing is I'm canceling things out. I generated 2 deuteriums here, but I used them here. I generated 2 helium-3s, but I used them here. I generated 2 hydrogen ones here, but I used 1, 2, 3, 4, 5, 6. So the net effect is I've put a net of 4 protons into the reaction, so 4 protons and 4 electrons coming in, and I've formed helium-3, and I have 2 anti-electrons, and I've generated 2 neutrinos, which have flown off and they're gone. And now if I take the energies from running this reaction twice, this once, that adds up to 24.7 MeV, and that is the energy that's being generated purely through the fusion reactions that we've outlined. Now if you'll notice, a result of the fusion reactions is leaving us with a little bit of antimatter. So it turns out stars are not only getting energy from nuclear fusion, they get a little bit of energy from matter-antimatter reactions, which I always feel like that's kind of cool. They're generating these anti-electrons. And remember, we've got electrons in that mix also. In the plasma, there's a bunch of electrons, and those anti-electrons react with the electrons there and can form high-energy photons. So in that reaction, the Q for the reaction where we're just forming photons, that's 4 electron masses, and that's 2.04, an additional 2.04 MeV. So 24.7 MeV from fusion, 10% or so of energy from matter-antimatter reactions, and we get a combined 26.74 MeV for the combined fusion and matter-antimatter reactions going on in the core of a star. That's a pretty effective reaction in terms of generating a lot of energy. So again, one more quick review of that. We started off with 4 hydrogens, which is the equivalent of 4 protons and 4 electrons. Now 2 of those protons come out as helium-4, and 2 of those protons along the way were converted into neutrons, and those 2 neutrons also are part of the helium-4. Now we started with 4 electrons, and 2 of those electrons remain, and they can be thought of as kind of matching up with the helium-4. But 2 of these electrons, now this is a little zigzag, along with these neutrons, these protons generated anti-electrons, which came back and combined with 2 of these electrons and formed a bunch of photons. Meanwhile, from this reaction up here, we're getting 2 neutrinos. So it's a bit of a zigzag. I'm not sure that was the best diagram. But you can think of these 4 electrons, 2 remain, 2 through this zigzag process are coming out as neutrinos. So here is our overall reaction for that. 4 hydrogens, here is my helium-4, 2 neutrinos, and some number of photons. I'm not going to try and count exact numbers of those here. And the Q value is 26.74. So to find out how effective or how much of the mass is being converted to energy, I can say I'm getting this much energy out, 26.74 MeV. I really only invested those 4 protons. So 4 protons combined are going to be about 4 atomic mass units, a little more than that, but approximately 4. And that worked out to be 0.00718, or 1 part in 139. So it's a little bit of an optimistic estimate here, but we're getting close to the point where maybe 1% of the mass is being converted into energy in this particular set of fusion reactions. So that's pretty significant, right? That's a pretty good mass to energy proportion that we're coming up with.